everyone. I am Jyoti Sharma, Assistant Professor in Electrical and Electronics Department at AKGEC Engineering College, and I am taking a lecture series on the topic Transformers, which is Unit 3 of the subject Basic Electrical Engineering, which is there in the first year with the subject code of KEE 101. Okay, so as I have taken first lecture on the transformer, in which we just discussed what is the definition for a transformer, what are its working principle, what are the classifications for the transformers, and what is the EMF equation of the transformer. With that, we have also seen what are the various ratios, right, we can see in a transformer. Likewise, the voltage ratio, current ratio, transformation ratio, which is given by K. Coming to the second lecture, what we are going to cover today, that is going to have the VA rating of the transformer and certain numerical based on that. An ideal transformer, what are the characteristics of an ideal transformer, how can we have the phasor diagram representing that complete working of the transformer. Then at ideal transformer being working on no load condition. Similarly, if it is a practical transformer, it is working on no load condition, what will be the differences that will be occurring. Then when the practical transformer is being loaded, then what is the difference in the working? How can we calculate the effective resistance, reactance and the impedance of the transformer? Okay, let us start with the VA rating of the transformer or the rating of the transformer. You just see the VA rating of the transformer. I am saying it as VA rating, right, or KVA rating. But generally, if you just see most of the machines what you are having, those are generally being rated in watts, kilowatts, right, HPs. So that means there we are incorporating the power factor of the load, right, because we know the kind of the load we are connecting. But in the transformer, once the thing is the kind of the nature of the load is not exactly known. In fact, any rating of any device, the power rating of any device, that depends upon the temperature rise which is occurring in that particular device. In a transformer, if you just see, right, so the rating of it should be decided by the temperature rise of it, and the temperature rise depends upon the losses which are occurring in a particular device, right. And what are the losses which are occurring in a transformer? The losses it encounters are either core losses or copper losses, right. So, if at all I see core loss, so the core losses of the transformer, that are voltage dependent, or I must say frequency dependent losses, right. Whereas, if I go with the copper losses, those are current dependent losses, right. Neither of the losses, they depends upon the power factor. So, the losses are either voltage dependent or current dependent. That is why the rating of the transformer is also being mentioned in VA, volt ampere, or kilovolt ampere or megavolt ampere. So, the basic unit remains the VA, that is apparent power rating of the transformer. It is not being rated in the active power, right. Okay, now coming to how do we give the rating of the transformer. So, if you just see, that is being given by V1 I1 upon 1000 or V2 I2 by 1000. That gives the KVA rating of the transformer. What is this V1 and I1 over here? So, V1 is nothing but it is the rated primary voltage, right, that means the input voltage. I1, it is the rated primary current which is flowing in the transformer, right. V2 is the rated terminal voltage of the transformer, and I2 is the rated secondary current which is flowing in the transformer, right. So, that gives the KVA rating. Now, just see a small numerical based on this. So, if at all I say a single phase 50 hertz transformer has 80 turns on the primary winding and 400 turns on the secondary winding. So, the net cross sectional area of the core is 200 centimeters square. If the primary winding is connected to 240 volts 50 hertz supply, so you need to determine first the EMF induced in the secondary winding, and second the maximum value of the flux density in the core. Okay. So, let us see what are the things which are given. If you just see, I am having N1. What is N1? The number of turns in the primary, and that is 80. Okay. the frequency of the operating given supply that is being given as 50 hertz, number of turns on the secondary N2 that has been given as 400, the number of turns that is given as 400, right, the area that has been given as 200 centimeter square, right, E1 that is the supplied voltage which is equal to the primary induced voltage that has been given, right, because it is being connected to 240 volts. So, we are considering it as 240 volts even. If that is so, what is the first thing being asked? The first thing being asked is the EMF induced in the secondary winding. It means I need to know how much is E2, right, how much is E2. To find E2, we know the relationship, we have just in the previous lecture we have done that E2 upon E1 which is given by the turns ratio, that is equals to N2 by N1, that is equals to K. And what is K? The transformation ratio, right. So, here I can easily find it out. I will know how much are the number of turns in the secondary and the primary. So, K, if you just see here, it is N2 by N1, 400 by 80. So, that is 5. So, 5 is my transformation ratio. So, obviously, the secondary terminal voltage, the secondary induced EMF, that is going to be 5 into 240, that is 1200 volts, right. Now, what is the next thing being asked? The second thing being asked is the maximum value of the flux density in the core, that means phi m, right. That can be very easily determined by the EMF equation of the transformer, right. And what is the EMF equation of the transformer? I can even have the primary EMF equation or I can have the secondary EMF equation. So, if at all say primary, so in that E1 is equals to 4.44 F phi m N1, right. Everything are known, I just need to substitute E1, that is 240, right, 4.44, frequency is 50 hertz, phi m I need to know, and number of turns in the primary that is being given as 80. So, just substituting that, the flux I will be having is 0.01351 Webers. So, this is what? This is the maximum value of the flux in the core. It is not the density, right. But when I say the maximum value of the flux density in the core, it has to be the maximum value of the flux divided by area, isn't it? Flux density is the flux upon area. So, just dividing it, the maximum value of the flux divided by the area, that is 200 into 10 to the power of minus 4, that is 0.6756 Webers per meter square, or I may even have that as Tesla. That gets me the maximum flux density in the core. Taking another numerical, if you just go for it, say for a single phase transformer having primary and secondary turns of 440 and 880 respectively. Determine the transformer KVA rating if half load secondary current is 7.5 ampere and maximum value of the core flux is 2.25 milliweber. Okay. So, what are the things being given to us? Now, the number of turns in the primary, how much is that? 440. Number of turns in the secondary, that is 880, right. Half load secondary current, that means when I say the rating of the transformer is V1 I1 or V2 I2, these all voltages and currents are pertaining to the rated or the full load rated values, right. So, when I say the half load rate secondary current of the transformer is 7.5, that means when the load has been halved, at that instant the secondary current drawn by the transformer, that is 7.5 amperes. Okay, if this is the given data, we need to just calculate further. The maximum flux which is being given is 2.25 milliweber, right. Now, what we need to know? We need to know the thing being asked is the maximum value of the core flux is this. Determine the transformer KVA rating. So, to have the KVA rating of the transformer, we just know that to know the KVA rating, I need to have it as either V1 I1 or V2 I2, isn't it? Divide by 1000, that will give me its KVA rating, isn't it? Right. So, what is much more convenient to me, right? I may first find how much is E2, because I already know the value of the secondary current in this, right. So, that is going to be 4.44 F, F is 50, phi m is 2.25 milliweber, into 880, right? So what is that secondary voltage I am having? That is 439.56 volts, okay, right? So I am already having V2 with me. This is nothing but this is very much equivalent to V2, right? Now what about I2? I2 should be the full load rating, isn't it? So in that case, I already know how much is the half load secondary current, that is 7.5. So obviously the full load secondary current of the transformer, it has to be the twice of it, that means 15 ampere, right? So the full load secondary current has to be 15 amperes. So what should be the kVA rating of the transformer? So you just see it is 2 into 7.5 multiplied by 439.56 divided by 1000, that means into 10 to the power of minus 3, that is going to get me 6.5934 kVA. So this is the kVA rating of the transformer given by, this is I2, this is V2, which are pertaining to the full load ratings, the voltage rating, full load voltage rating and the full load current rating of the transformer, right? Now moving on to a very interesting and very important topic, that is ideal two winding transformer, right? We have studied a lot about transformer, but what is this exactly ideal transformer is? What we expect from a transformer, right? So in an ideal transformer, what is going to happen? So certain characteristics are there for an ideal transformer. Likewise, the very first one is the winding resistances are negligible, right? Those are not considered. All the flux set up by the primary that links with the secondary, that is all the flux is confined to the core itself. That means the complete flux produced by the 100% of the flux produced by the primary that links with the secondary. I don't have any leakage flux, okay. Third point, the core losses are negligible. There aren't any core losses. That means no eddy current loss, no hysteresis loss, right? As windings are also, we are considering winding resistance is 0. So obviously the copper losses, those are I square R losses, those are also 0, right? And core has constant permeability. That means magnetization curve is linear. Constant permeability, that too a very high permeability. It means what? That the transformer just requires a very negligible current to get magnetized, isn't it? If the permeability of the core is so high, is very high, it means that it is getting magnetized very easily. So it requires a very small current to establish the flux in the core, right? So these are the characteristics for the ideal transformer. Now just see how the transformer will behave, this ideal transformer will behave if it is made to work on no load condition, and we also see the phasor diagram of it. So let us see the transformer, right? So this is our transformer which is being fed with an alternating supply, right? And the load terminals, if you see the secondary terminals, these are open circuited. So there is no load which is being connected to the secondary. Fine. So in this case, this is an ideal transformer. So there is no winding resistance in it. So my V1 is equals to E1, right? V1 must be equals to E1. Also V2 must be equals to, in magnitude, it must be equals to V2, right? Now the same thing will happen, you know, as the permeability of the transformer is very high. So what will happen? I don't have any load, so that the transformer has to make up with that load, right? So it doesn't have to make up with the core losses as well, right? So what it has to do? For what the transformer will draw the current, right? It doesn't have to make up with the load, it doesn't have to make up with the losses, it doesn't have to make up with the drops even. So the transformer will draw a very negligible current that we used to call it as a magnetization current, right? We used to call it as magnetization current, and this is a very small current which is just required to magnetize the core or to establish the core in the flux, to establish the flux in the core, right? So because the nature of the supply is alternating, the current which will be flowing is also alternating, and this current is very much sufficient to establish the flux in the core. So once the flux which is alternating, it will induce an EMF in the primary, that what we used to call it as E1. The same flux links with the secondary, it will induce an EMF in the secondary winding also, which we call it as just E2. as there is no load being connected on the secondary terminal, obviously this V2, the terminal voltage what we are getting, that will be very much equal to this E2, and there will not be any secondary current. I will be having I2 as 0, right. So, this magnetizing current what we are discussing, this magnetization current is just, it is just a negligible current which is just required to magnetize the core, and this used to be generally 2 to 3% of the full load primary current of the transformer. Say, if at all, for an example, if at all I say the primary current taken by the transformer at full load is say 5 ampere, right. So, what will be the no load current taken by the idle transformer? So, it has to be just 2 to 3% of it. So, 2 to 3% of it is near about 0.1 to 1.15 ampere. So, this is a very negligible amount of current, right. How to have the phasor diagram, if you just see. Now, this is the very basic for drawing any phasor diagram of the transformer. If you just see, the phasor diagram starts with the quantity which is being common to both the primary winding and the secondary winding. So, what is that quantity which is common to both primary and secondary? That is flux, right. So, we need not to change it again. So, that is why we used to have the flux as my reference phasor. Then, obviously, this magnetizing current is the current which is just required to establish the flux in the core. And the nature of the flux which is being produced, this is because of the reactive winding, right, as the winding resistance is 0. So, now the current taken by the primary winding is purely inductive. It means for an inductive circuit, what used to happen? The current used to lag the voltage, right. And in fact, this current, as this is the current which is responsible for the production of the flux, it will be in the same phase as that of the flux, isn't it? So, Im would be in the same phase of that of flux. V1, what is V1? That is the supplied voltage. Now, we just discussed that as now this winding is purely inductive, because we have seen for an ideal transformer the winding resistance is 0. So, that for a purely inductive circuit, the voltage should lead, or I must say the current should lag by 90 degree. That is why your voltage V1 would be exactly 90 degree leading the Im. Fine. Now, what about E1? We just say that V1 would be equal to E1, but actually what is E1? E1 is nothing but it is the self-induced EMF, and any induced EMF will be acting according to the Lenz's law. And what is the Lenz's law? According to Lenz's law, the induced EMF will oppose the very cause producing it. And what is the very cause producing this induced EMF? That is nothing but the supplied voltage, right. So, in this case, your E1 should oppose, in phasor obviously, should oppose this V1, that is being shown by the opposite phasor. So, your V1 is just in opposition with V1, right. Now, once again E2, what is E2? E2 is nothing but that is again an induced EMF, right. So, where should be E2? It should be in the same phase as that of E1 or in phase opposition with V1, right. In fact, I may write this E2 is equals to V2. So, this is the complete phasor diagram of an ideal transformer working on no load condition, right. Okay. Now, going for the practical transformer working on no load condition. Now, what will happen if that ideal transformer is being replaced by a practical? Now, in this case, once again, this is working under no load condition. That means the secondary terminal is still open circuited, right. Now, once again, now when you give the alternating supply to the transformer, in that case, now the transformer, once again, it does not have to do much of the work, right. It does not have any load, right. So, it does not have to make over with the drops, it does not have to make over with the load. So, what is the work it is going to do? It has to, but this time, as this is a practical transformer, it has to make over with the losses, right. Which losses? The two losses which we just discussed. The iron loss, the copper losses, right, or I just say that is I square R losses, I square R losses, right? These are copper losses and also the iron loss, or I may just call it as Pi, right? So both the losses it has to make over. Now during this, if you just see this I square R loss, what is this I square R loss? This is current dependent loss, and at the no load condition, the current taken by the transformer is very negligible, right? So the losses I square, the squaring of that loss, the current, that will give me a very negligible copper loss, right? Or I can just I may just not consider these copper losses, right? Negligible losses. Whereas iron losses, these are constant losses, right? These are frequency dependent, so these would be there. So the transformer will draw the current which is just required for doing two works, right? For doing which work? Now the current taken by the transformer, which I am calling it as I naught, will be performing two functions. What is the first function? It will be magnetizing the core as it was being doing for the ideal transformer. This is what is required, right? So it will draw the current which is required to magnetize the core or establish the flux in the core, and also it will require a component which will make over with the core loss component, core losses, right? As we just discussed, it has to overcome with the copper losses also, but the copper losses are negligible at no load condition as the current used to be very small. So I must say the total no load current taken by the transformer should be the phasor sum of the magnetizing current and the working component, right? Magnetizing current just required to magnetize the core, working component required to make over with the core losses, major core losses with a very negligible amount of copper losses, right? So just see the phasor diagram of it. Now the phasor diagram, if you just see, it is very much symmetrical to what we have done in idle. Now once again, this is the reference phasor which is being given by phi m, right? Now once again, this is I mu, which I also call it as I m, magnetizing current, right? Which will be once again in same phase as that of phi m, because this is the current which is responsible for the production of the flux in the transformer, right? So that will be in the same phase as that of phi m, okay? Now the working component, if you just see, once again, what about V1? V1 will be once again 90-degree leading, right? Because this is just purely inductive current, right? Once again, the winding resistance is not being considered here. So in this case, once again, V1 would be 90-degree leading this current, right? Now as these working component, this is just the core loss component which is voltage dependent. So it will be just in phase with this voltage, right? And the phasor sum of Im and Iw will give us this I naught, the no load current. Once again, the value of this no load current used to be very small, right? How much? It used to be generally 3 to 5% of the full load primary current of the transformer, 3 to 5%. Once again, it is very less, right? But the difference between idle and the practical is that in case of idle, it was just Im, which is very much negligible just to magnetize the core, and in case of practical, it is the phasor sum of the magnetizing current and the working current. What is working current being required? For makeover with the core losses, right? Further moving with this, I can, in fact, we can see this is the no load current, or I must say the primary current taken by the transformer, right? This is the primary voltage. So the angle between this voltage and current, what you call it as phi naught, is nothing but the no load power factor of the transformer. How can I give that? So cos phi naught can always be given as Iw by I mu. Also I naught, if at all I say, how can I give the magnitude of this no load current? That obviously, as it is the phasor sum, it can be given as under root of Iw square plus I mu square. Individually, by this relation, I can even give that Iw is nothing but I naught cos phi naught, I mu is I naught sin phi naught, I naught is the phasor sum, so under root of Iw square plus I mu square, cos phi, Iw by I mu. Now as the angle is phi naught, so power factor will be cos phi naught. Also core loss would be given by, you know that at no load condition now the power being taken by the transformer, that is all going in the core loss, right? And what is the power being taken by the transformer? The input voltage V1, input current, the no load current, the power factor, the no load power factor. So it has to be V1 I naught cos phi naught. So that gets me the core losses. So I may just say that for a transformer working at no load condition or open circuit condition, that gives us the core losses of the transformer or the constant losses of the transformer, right? Okay, just take an example. Say a transformer takes a current of 0.8 amperes when its primary is connected to 240 volts 50 hertz supply with the secondary being open circuited. If the power absorbed is 72 watts, determine the iron loss current, the power factor on no load and the magnetizing current, right? So you just see the no load current that has been given as 0.8 ampere, right? And the core loss at no load condition, the power taken, that is core loss, that is given as 72 watts. If the power absorbed is 72, so no load pay, the power draw taken by the transformer at no load, that is nothing but the core loss we just discussed, right? So that is, yeah, core losses are 72, right? How do we give the expression for these losses? That is being given by the primary voltage, the no load current and the no load power factor V1 I naught cos phi naught. So from here I can have the no load power factor of the transformer, that will be given by the core loss divided by V1 I naught, that is 72 divided by 240 into 0.8. So the no load power factor, that becomes 0.375. Okay. Now this is the no load power factor being asked. The second thing asked is the power factor on the iron loss current. Iron loss current means the iron loss component of the current, no load current, right? So the iron loss component of the no load current, which we call it as working component IW, right? That is, so for finding IW, I may be just getting it as, we just know in the previous slide also, this is the cos, IW is I naught cos phi naught and I mu is I naught sin phi naught. So the cos component of the no load current will give me the working component of the current. So that is 0.8 into 0.375, that is 0.3 ampere. Similarly, the magnetizing current, which we call it as either Im or I may be either calling it as I mu. So that will be given as I naught sin phi naught, the sine component of it, right? So that will be given by 0.74 ampere. Now moving on to a very significant topic, that is practical transformer on load, right? Now the transformer is being loaded. So what are the differences? It will be occurring when it is being at no load condition, right? So when the supply voltage V1 is given to the transformer primary winding, the primary current I1 flows through the windings which produces the maximum flux phi in the core, we know that. When the secondary winding of the transformer is loaded, the secondary current I2 flows through it, right? So the secondary current, it also sets up its own MMF. What is that MMF? N2I2, right? It sets up its own MMF and its own flux phi 2 which opposes the main or the primary flux phi m. Therefore, the resultant flux and the primary induced EMF, it also decreases, right? If you just see from the diagram as well, right? Once you give the primary voltage, I know this time what you have done, you have loaded the transformer, right? Once you load the transformer, everything is same. I have given the primary voltage. With that, I will be having now, initially when the transformer is not loaded, the transformer was drawing the no load current as it is, isn't it? That is very much required. The no load current is required for what? For makeover with the core loss and to make over with the to magnetize the core, that is itself is there. Now what is happening? That is very much sufficient. This I naught is very much sufficient to establish the flux in the core so that I am having even, right? That same flux when links with the secondary, it induces the secondary induced EMF, which is a mutual induced EMF, what you call it as E2, right? Now, when you connect the load across these terminals, I'll be having a secondary voltage appearing across these loads, which you call it as V2. And obviously, this circuit is completed. So, I'll be having a secondary current flowing, which you call it as I2. Because of this I2, obviously, now I'm having how much turns in the secondary? I'm having N2 turns in the secondary, right? And I'm also having secondary turns as N2, I'm having secondary current as I2. So, I'm having N2 into I2 as the secondary MMF being produced, right? Now, obviously, this secondary MMF will produce the secondary flux, right, which you call it as phi 2, which will be acting in the opposite direction to the main flux. What is the direction of the main flux? If that has been assumed towards the right hand side, the flux produced by the secondary MMF, that will be equal to, that will be flowing in the opposite directions towards the left. So, both of them will cancel out each other, so that the resultant flux would be reduced, isn't it? So, if the resultant flux reduces, so the net EMF on both the sides will also reduce, right? When the supply system, when this difference occurs between V1 and E1, once this induced EMF decreases, there will be a difference between V1 and E1, right? Because this difference increases, this V1 and E1 increases, V1 minus E1 increases, now the transformer feels the load. And now the transformer, it draws an extra current from the supply. That extra current is what you are calling it as I2 dash, right? To make over with that difference V1 minus E1, right? And you call this I2 dash as the reflected load current. This current is actually equal in magnitude to that of I2, but in antiphase of I2, right? We will be seeing what is the relation. The current I2 dash now set up of extra flux phi 2 dash in magnitude. Therefore, the MMF N1 I2 dash and N2 I2, they cancel out each other, right? So, we can say that the magnitude and phase of the load component of the primary current depends upon the type of load. The net flux passing through the core, that remains constant whatever the load conditions if we neglect the primary and secondary leakage fluxes, what we just see over here, right? The phi is the main flux produced by the primary winding. Because of this loading effect, the demagnetizing MMF, that produces the flux phi 2, which cancels the main flux, so that the main flux magnitude reduces. With that, when phi m reduces, obviously the induced EMF E1, that also reduces. If that is reduced, the difference between V1 and E1, that increases. When this increases, the transformer draws this extra current I2 dash to make over with this difference, right? With this extra current, the transformer now once again produces an extra flux, which you call it as phi 1 dash, in the same direction of the main flux and in the opposite direction of the phi 2 dash. This means phi 1 dash must be equals to phi 2 dash, so that both of these fluxes cancels out each other and the transformer is remaining with its original flux in it. That's why the transformer is also being called as a constant flux device, because at any loading condition, the transformer flux is not going to get varied, right? So, the next topics and its phasor diagram will be continued in the next of the lectures. Thank you very much.